Okay, let us study chapter 14. This is the last chapter of this course, and we arrived at the position to study the classical field theory. In the previous chapter, we have studied the normal modes behavior of the loaded string with the arbitrary number of beads distributed on a string with equal spacing. The result can be applied to the continuum limit, and we will construct the classical field theory to describe the wave nature of this continuum limit. And this is very, very important because this classical field theory is directly related to the extension into the quantum mechanics. In addition, it can further be generalized to the quantum field theory that is well advanced in even comparison with the quantum mechanics. So this is a basic building block of those advanced physics. However, it is stemmed from our elementary study regarding the diagonalization of a Hermitian matrix. And today we will construct a systematic approach to study the continuum limit and the more detailed study regarding the Hilbert space. First, we consider the loaded string. We have n beads, n identical beads with the mass m. Thus, the number of beads is n, so that the total mass of the string, loaded string, is considered to be capital M. If we distribute n beads with equal spacing between the 2 points on the wall, x equals 0 and x equals L, if I put a single bead, we have 2D. And if I have three beads, and the spacing will be d. So n plus 1 d will be the length, capital L, of the loaded string. The linear mass density, this is a linear mass density of the loaded string will be capital M divided by the length of the string, and that is n times m over n plus 1 times d. As n goes to infinity, this ratio n over n plus 1 will reach 1, and small m over d will be the linear mass density. This is the eigenfunction, this is the eigenvector for n beads distributed with equal spacing on a string, and this satisfies normalization for R dagger, and S is delta RS. That we have already proved. We noticed that this phase has a common factor R. This R appears at every phase, and the front factor, it begins with 1, 2 to the n. We used the index k, the row index of this column vector. In the continuum limit, the number of elements will go to infinity, and we keep the total mass to be m. So this mass, as n goes to infinity, this mass of each bit will decrease to keep the ratio the same. Okay. When we introduce a continuous variable, this is a kind of sequence. As d goes to 0, this xk, this sequence xk becomes a continuous variable. So we introduce a real variable x to identify the column, the row number of this column vector. And we'd like to rewrite this one as a function, because this psi r, for example, if I have this kind of form, psi r has equal spacing with d, and if we decrease this d to be 0, then this distribution of this graph will lead to a continuous function. So we would like to re-express this scalar product between the two eigenvectors in terms of the integral of two eigenfunctions. Okay, so these signs can be expressed as a sign k r pi, where r goes to r runs from 1 to n, and for each r, k, this is the row number, k runs from 1 to n. All right, so we rewrite this kd. So if I multiply d in the numerator and the d in the denominator, this kd becomes the position of the longitudinal position. So this one becomes x. And this denominator n plus 1 multiplied by the spacing will be the length of this string. So we would like to represent this column vector by a function. This is sine r pi x, sine r pi x over L. And let us consider the overall normalization, square root 2 over n plus 1. If I multiply d and divide by d in the numerator, then we have this one to be the length of the string. So vector of square root 2 over L is vectored out, and then we end up with additional vector square root d. And actually this d is the difference between the adjacent b's, that is the equal spacing itself. So if I consider the orthogonality of the two eigenvectors, we have these relations. This final result was Kronecker delta Rs. And multiply d, both numerator and denominator, it becomes L, a factor of 2. And as we have shown here, this is replaced with r pi x over L, s pi x over L. And we have equal spacing d, and this additional d. This d is included to find out the length, but this d is migrated to here. So this summation in the limit n goes to infinity becomes just the integral of this one. And this one is replaced with dx, and this one is xk is replaced with the continuous variable x, and then this is over a vector. So dividing these two factors into a square root, this is the eigenfunction. And in the bracket notation, this integral can be written in this form. Psi r this is identity and psi s. We'll find this is integral psi r x and x psi s. You know, this is x and this is reversed. So r x star integral. Okay? And actually this is psi r s. And it was delta s. So this notation can also be used for the continuum representation in terms of the eigenfunction. So this one can also be used for the eigenfunction and eigenvector. So we'd like to consider the normal coordinate. The coefficient of this eigenvector in the discrete form was the normal coordinate that contains all of the time dependence. And we recall that the characteristic frequency is exactly determined in this form. Here, as n goes to infinity, the first value that becomes the minimum at r equals 1 becomes a very tiny value. As n goes to infinity, it approaches 0. So the minimum characteristic frequency reaches 0. However, even though n goes to infinity, this maximum value will be obtained when r is n. And we know this is just the sine half of pi as n goes to infinity. That is just 1. So we find that the characteristic frequency has a maximum value. It is a fixed. So we can say it is a cutoff frequency of the normal modes. Even though n goes to infinity, it can never reach infinity. We can compare our result with the case of a Schrödinger equation. The separation of variable can be used to solve the Schrödinger equation. The time-dependent Schrödinger equation is written in the form. In comparison with the case of the string vibration, we have only a single first-order derivative with respect to time, although the spatial derivative of the second order, that is the same. Anyway, we can make use of the trial solution, which is e to the minus I omega t and e to the ikx. So it is a separated. The time part and the spatial part are separated. Substitute into this partial differential equation, we obtain this is just composed of two parts, the time-dependent part and the spatial components. And the final result will be the spatial component must satisfy the boundary condition. This is the case of infinite potential well. This potential becomes 0 between 0 and L, and potential otherwise becomes infinity. That means the wave function at x equals 0 and L are both vanishing. With the constraint of this boundary condition, our x-dependent part, which is a linear combination of cosine and sine, kx, we find it is expressed in terms of the eigenfunction for this string vibration that is identical. However, the time part is rather different. We can consider further in detail that this is time-dependent Schrödinger equation. We substitute the trial solution with the factored form into the capital T is the time-dependent factor and capital X is the spatial components. And if we substitute, the x and t are factored out because these derivatives does not change this x and t dependent piece. If we divide these equations with the x times t, this part, left-hand side, will purely depend only on t, and right side depends only on x. Because it depends on t only and x only, these two values must be independent of both x and t. Therefore, we introduce an eigenvalue E that is constant that is independent of both t and x. This part can be solved. This is just the first order differential equation. So we have exponential minus I over h bar et. You must remember that there is no plus sign in here because this is not a second order equation. It is just a first order equation. It is completely determined. So only the negative sign exists and the positive sign does not exist at all. And the spatial part has differential equation that's quite similar to the harmonic oscillator, except that this x is the time derivative is replaced with the spatial derivative, and the answer is a linear combination of the exponential ikx and minus ikx. Because it is a second order, we have two contributions. We can express it in terms of cosine sign in a similar manner, but introducing the boundary condition that the wave function must vanish at both endpoints, we have sine n pi over Lx. Combining the time-dependent factor, we have obtained this, where energy is completely determined by this formula, this Hamiltonian. So here we find that this coefficient Cn of this expansion can be found by projecting the nth component of the eigenfunction. Remember that this allowed value for n is only 4, 1, 2, and so on. If I substitute n equals 0, it is not a state. N equals 0 is a psi equals 0, so it is not a state at all. This is nothing. We remember that the orthogonality of the eigenvector is given in here, and our derivation of the continuum limit guarantees that this value should be the same. But we can check this if it is true by explicit calculation. So we can rewrite this product of sines as a difference of cosines, and integral gives this. When these r and s are different, this is a multiple of pi. Every sign must vanish. In case r equals s, we have L'Hopital's theorem to find this factor is a pi. Therefore, it is 1 for r equals s. That means that the integral of this, the scalar product of two eigenfunctions satisfy the scalar product of two eigenvectors for finite discrete cases. Anyway, we can construct a completeness relation by making use of this eigenfunction. If it were an eigenvector, the direct product was identity operator. But we remember the psi of x can be integrated from the psi of y by multiplying delta x minus y. We substitute this here, and this expansion is natural for the expansion of the wave function in terms of eigenfunctions. So This is a consistent way of describing the continuous completeness relation for this eigenfunction. Right. So this eigenfunction and eigenvalue, they are almost the same. In a similar manner, we expect that this one is x and y because we can also introduce this kind of psi of I and psi of j can be expressed in terms of the identifier for the eigenstates. Let us check it on the next page. All right. So eigenfunctions has the unit normalization if I have a square root 2 over L, and that is completely exactly the same for the vibrating string, and in the quantum mechanics problem, the infinite potential problem, as far as the eigenfunction is concerned. But as I told you, time-dependent contribution, time-dependent factor, the normal coordinates are completely different because the Schrading equation has a first-order time differential, first-order differential equation in terms of time, but the wave equation for the string vibration is a second-order partial differential equation with respect to time. We now extend this coordinate of a bead at the kth bead and at this time-dependent position, displacement, and we introduce time-dependent scalar field, replacing this k. With k, we introduce the x of k, that is k times spacing, and as d goes to 0 and with n goes to infinity, this xk became continuous variable x. So instead of writing qk, we replace this q with phi and k with x. So this is a scalar field that is a function of both the time and space. Thus, the string vibration is described by this function, time-dependent function. This function is a scalar field. And we already obtained that this one is completely expressed as a linear combination of eigenfunctions. And those eigenfunctions are given in here, right? And all of the time-dependent vector are contained in here. So this is a kind of the separation of variable, and it is already we have proved it is true. And how can I obtain this normal coordinate? This is we can obtain this one because this is a kind of, if I make use of bracket notation, phi is psi of r, and its coefficient is sum over r. And this is actually the normal coordinate. This is normal coordinate. This is independent of time. And if I rewrite this one, so what I do is just make an x projection. So x projection. And this is a phi t of x equals the sum of r at r of t and psi r of x. This is this. Alright? So finding out the normal coordinate and its a time derivative can be obtained in such a manner. So we can review the bracket notation for the Hermitian operator. Hermitian operator, and this is eigencat for Hermitian operator. Then its own eigenvalue is always real, and those eigenvectors are always perpendicular to. So we can construct a normalized eigencat, and this eigencat expression can also be used for the eigenvectors if I project out to the column indices. If I project onto the variable x, then I can obtain the eigenfunction. So eigenvector approach and eigenfunction approach they are equivalent for the Hilbert space. So if A is a Hermitian, its dagger is the same, and we remember that AR is a real number, and we can always fix the normalization to have the uninormalized eigencats. If I make use of function that is eigenfunction, what we do is just project out the position space from the eigencat. So the eigencat has a general property, and this is a specific property when we want to carry out the scalar product. We have some notation. For example, scalar product of two eigenfunctions can be made as an integral, and that can be done by making use of completeness relation. And additional completeness relation is for the projection onto the function space, the projectile, the x dependence. Here I have summarized the tools for this. You remember, this is another completeness relation for the eigenfunctions. If it were eigenvectors, it will be psi r, direct from to psi r dagger, and becomes identity matrix. Okay. All right, so if I make use of this expansion in terms of eigenfunctions, what we gain, or what we obtain for the coefficient is the time-dependent one that is called the normal coordinate. Only the normal coordinate has a pure time dependence, and the eigenfunction does not have any time dependence at all. And then this is time-dependent scalar field. So orthogonal relation can be used, expressed in this way. That is eventually the same as delta chronicle delta Rs. If I want to make use of eigenfunction, what I insert is identity that is integral of the direct product of x cat. Then what I obtain is psi s of x and this opposite, so this complex conjugate. Therefore, if I want to collect the coordinate, normal coordinate, what I want to do is multiply the complex conjugate of the eigenfunction to the scalar field and integrate over the space. In a compact form, with in terms of the bracket notation, it is psi r projection onto the scalar field phi. Remember, scalar field phi can be expanded with, by making use of the identity operator. This identity operator can be rewritten by making use of the completeness relation for the eigencats. So direct product of the eigencats summed over all possible states, all possible quantum states will lead to this, and that is equivalent to the previous notation. In the functional form, if I multiply this one to the above equation, what I obtain is the field phi, and this is function, that is expansion in terms of the eigenfunction. Let us construct a Lagrangian in the continuum limit. First, let us write down the kinetic energy. Kinetic energy is written in this form, 1/2 mass times qi dot squared. And we remember qit is I times d is xi, and that will be replaced with x, and this will be replaced with a scalar field, and time dependence, and coordinate I is replaced with the continuous variable with position, right? Therefore, the time derivative of this coordinate will be replaced with the partial time derivative of phi. Because phi is a function of both the t and x, what we want to do is just to keep the index position, keep the position the same, and we take the derivative with respect to t only. Okay? Therefore, in the summation, we divide d and multiply d. Then we find this is m over d is the mass density, linear mass density, and this is the partial derivative. As I have already stated, this is to be replaced with the partial time derivative of the field squared integrated over x. The potential energy for the B's will be expressed in terms of the summation, and we insert this d inside. Then we have to multiply d because it is a single power, it is double power. So this d is actually, as we have done, this d is the differential of the displacement. So this one is replaced with the dx in the continuum limit, and this is the difference of the coordinates divided by spacing. That is x partial derivative of the field with respect to x. Therefore, the Lagrangian is the kinetic energy subtracted by the potential energy, and the kinetic energy is 1/2 linear mass density and partial time derivative squared. And potential energy is written in here, so minus tension of the string and the partial derivative of the scalar with respect to the position squared. This is an integral of integrand over x. This integrand is called the Lagrange density function. Okay, we have constructed the Lagrangian in terms of Lagrangian density, and the Lagrangian is the integral of Lagrangian density function over x. This is for the continuum limit expression for the Lagrangian for the vibrating string. We will extend this method to the vibrating membrane and vibrating subvolume. Anyway, this Lagrangian density function for this vibrating string was expressed in terms of this. So we will next consider find out the solution for the specific problem. This problem is for the picking up the guitar string. This is the initial state, and then after this, at the t equals 0, the string was in this position, and you leave your hands. Then you will find that it will oscillate, and our final result will be a linear combination of various normal modes. This is so-called Fourier expansion. But before we study that one, we consider the eventual form of the equation of motion in the continuum limit first. The equation of motion for the discrete beads loaded on a string was written in this form. If we reorganize this, distribute this to 2 times qk into here and there, what we find is difference of qk plus 1 minus qk and qk minus qk minus 1. If I pull this d in the denominator, we will find this one. Okay? And then we have additional d in the denominator. That means that we have multiplied the d on the left side. The mass is also multiplied to have mass over spacing. The mass over spacing is the linear mass density. We remember the second order derivative will be, because the qk is to be replaced with the scalar field and xk, which is a continuum variable x. We notice that this first term in the numerator is actually to be replaced with the scalar field at position xk plus 1. And this is the same thing except that position xk. We know the spacing is d, so the d is to be replaced with delta xk. In the limit delta xk goes to 0, this is the partial derivative of the field with respect to x. And next term is the same partial derivative of the field with respect to x, except that there is a spacing between these 2 points by delta xk. That means that this is the first order derivative of with respect to x, and the difference and ratio take this d taken to be 0, then this is the second order derivative with respect to x. As a result, this is the second order derivative with respect to time, and this is second order derivative with respect to position. Over vector is a linear mass density, and this is tangent. If we divide this equation by tangent tau, what we obtain is rho over tau and this expression. This is exactly the same as a wave equation if we define the speed of the wave propagation to be square root of tension over the linear mass density. Orthogonality of the eigenfunction can be applied to obtain the expansion of this form. And we recall that the normal modes can be obtained as a linear combination of sine and cosine. This is the vibrating string. This is not a quantum mechanical infinite potential well that has only the single exponential factor. Time derivative of this normal coordinate will be this. We remember the initial condition, the field. Time derivative of field is always 0. But another initial condition is the phi of t equals 0, x is of this form. So using these two constraints, we can determine the all of the normal modes, normal coordinates, okay, by making use of this integral. We remember that phi dot is 0 for all over the space. As a result, because of phi dot at t equals 0 is beta omega r, because if I substitute t equals 0, it is 1. Therefore, beta, all of the beta becomes 0 because of this condition. Second, we have this condition. by making use of this, we can find out that eta r, because of this condition, we have only the omega contribution to be alpha r cosine omega rt. All right, the final procedure is to determine the coefficient of alpha r that are both independent of time and space. This one can be obtained by substituting 0 to the normal coordinate. That means this integral should be evaluated. This integral, if I look at this initial condition for phi 0 at t equals 0, it is symmetric with respect to the central point. Okay, symmetric. For example, r equals 1, that is the ground state, we have non-vanishing contribution because there's both vectors are symmetric. And n equals 2, we have this kind of form. This is anti-symmetric on the exchange with respect to this axis, central axis. And n equals 3, we have also symmetric form to have a non-vanishing contribution. As a result, alpha r survives only for the odd values, 1, 3, 5, and so on. The resultant integral can be obtained to determine the coefficient. And if you follow the calculation, you will find the coefficient. And as we already stated, it is proportional to the cosine, and the spatial component is the sine. This integral can be evaluated by making use of this integral table, and we can also derive those integrals in terms of this simple integral in terms of exponential IAX. After evaluating this, you take the imaginary part to have the sine contribution. But what happens to the case if I have x sine something? That can be obtained by taking the derivative with respect to a. Because this expression, if I take the derivative with respect to a, we have over vector x. Sure, I have I also that is divided. The method can be used to find out the integral table for this. This kind of method is quite useful to find the various mathematical formula. For example, gamma function can be evaluated in such a manner. Elementary integral for exponential is 1. We introduce a scaling factor a that is positive. Then we can rewrite this one. We scale this ax. We define ax by changing the variable to t. Then we find it is 1 over a. By taking the partial derivative with respect to a, we can construct a relation for the gamma function that you are quite familiar with. Now let us consider orthogonality of eigenfunctions of a Hermitian operator. The equation of motion for the vibrating string was a kind of the second order partial differential equation. And if I introduce the operator method using bra and cat expression, our calculation for the Hermitian matrix eigenvalue equation and eigenfunction case, in any case, they are all well expressed. So the compact expression can be achieved if I introduce the bracket notation. And the projection onto a matrix space can be made by projecting the row or column element, row or column index for the given Hilbert space, or if I consider the continuum limit, then we can project out the x dependence, or if I consider the momentum space wave function, we just pull out the momentum space wave function by projecting out the momentum eigenstate, that eigencat, that is p. Anyway, in general, this kind of method can be used regardless of using the matrix representation or functional representation. We have a right way, very simple, compact way to find out the eigenvalues are real, and any eigencats that has the different eigenvalues are orthogonal. And even though there are degeneracy, we can always find a linearly independent but orthogonal eigencats. In general, in a function, if I take the continuum limit, the problem reduces to solving a second order linear differential equation of a self-adjoint form. We say this kind of second order differential operator to be self-adjoint. The orthogonality of this eigenvalue problem is, we call it the Sturm-Liouville problem. Okay, there are three functions: p, that is real and differentiable; q is a real function; and w, we call it a weight function; and lambda is the eigenvalue. And this w, q, and p, all three functions are real. And we allow this solution y to be a complex number, but that depends only on the real variable x. Let us define the scalar product between the two eigenvectors, but we can always use the eigencat expression. Bracket notation is quite useful. This is very compact. But if I introduce integral, that should be, the left-hand side should be a function of x with the same index, but with the complex conjugate. The right side one should be a function. This one can be understood as we insert identity operator, and that identity operator is integral over dx with weight function x, and then which n, and this is a psi n of x, and this gives a psi m star of x, and we have additional factor that is weight function. That does not appear in the elementary problem, but in many cases we have the weight function. For example, Hamid polynomial has a weight function. Sure, we can redefine this one. We can absorb this one by square root of w and absorb that factor into the weight function, but mathematically it is more compact. We have a special boundary condition. There's a linear combination of a solution and its derivative at each endpoints vanish. But we are more interested in the simpler case, especially the vibrating string or the infinite potential wall problem. We have this one is exactly 0. Endpoint wave function vanishes. We have this kind of solutions, this kind of problem that is related to the resonating pipe, the sound wave has this kind of a structure, right? So derivative at the endpoint vanishes. So, however, in general, mathematically, this one is also allowed. But today, we are interested in the case this function itself vanishes at both endpoints. All right. Let us write down the eigenvalue equation for two different eigenvalues and corresponding eigenfunctions. We'd like to find out the scalar product. So in order to find out the scalar product, we multiply the complex conjugate of the second one. Complex conjugate of second one and integrate over a from a to b. Here, on the previous page, we have written a equals alpha and b equals beta. All right, so it's better to write to avoid confusion. Beta, alpha, beta, beta, alpha, alpha. So many. Beta, alpha, beta, alpha, alpha, beta. Okay. And then the second equation is take this complex conjugate of the second equation and multiply psi n to the right side and integrate in the same region. We rewrite a, the left side of a is this, and right side of a is this. Right? And second one, complex conjugate and multiply with the psi n. We find that these two, because this is quite important, P, Q, W, they are all real. P, Q, W, they are all real. Only if they are real, we have this kind of relation. And because this one and this one, they are the same, if I subtract, then these two vanishes. And we end up with, on the left-hand side, the difference of this and difference of this. And left side is like that, and right side is a factor. We have the difference of the eigenvalue and the complex conjugate of the eigenvalue of m. And the left hand side, this one can be written in the form, we can make an integration by part. So this one can be written in the form, the derivative of these two factors, and then subtracted by the derivative. And the second piece have this form. We find that this contribution exactly cancels, and remaining piece is just a total derivative. Total derivative can be integrated out, and we can substitute the value at the end points. So this one and this one. If we consider the simplest case, that we consider this value. Function itself vanishes at both ends. Vibrating string, function alpha equals 0, x equals alpha, and x equals beta equals L. These two functions vanish. So this one at alpha and beta, this one at alpha and beta completely vanishes. So left hand side is exactly 0. Okay, therefore, this is an expression in terms of Wronskian, and in general, we can prove that left-hand side vanish in more general case. Anyway, in our case, we just simplify our analysis by considering the vibrating string case. This is a completely 0, and pipe case, derivative vanishes, so we end up with this expression. And this is actually the scalar product of state m and n. All right. So we end up with the previous analysis. We don't repeat. If we find this kind of expression, if we substitute r equals s to find out that this, because it's a positive, and this is, if n equals m, this is complex number, absolute value squared. Because w is positive, the integral is a positive definite. It can never be 0, and therefore this one should be 0 for the index. Two indices are the same. That means the eigenvalue is real. And then once eigenvalue is real, we can erase this part and the difference of the real eigenvalues. And when the eigenvalues are different, then this one can be divided, and we will find that eigenvalues are different, then the two different eigenstates have vanishing scalar product. And then in case we have degeneracy, we have developed a way to find that these any degenerate states have the number of dimensions that has the orthogonal eigenstates. In this case, it's orthogonal eigenfunctions, right? As long as the dimension is available. Next, we consider the action principle. We recall that by applying the least action principle, we can construct the equation of motion. And that equation of motion was the Euler-Lagrange equation. The difference between the current situation and previous one for the single particle case, in the field, we do not have, we do have the Lagrangian. However, it can further be expressed in terms of Lagrange density function. And we have a double integral instead of a single integral over time. That is the quite big difference. But remember, we first have to find out the variation of this Lagrangian density, because we want to compute the variation of the action. All right, and then we have some constraint. As far as the t integral is concerned, the integral from t1 and t2, we do not allow the variation at both endpoints for time, right? That is the same as before. We have additional boundary conditions because these vibrating strings are fixed at the end. So we do not have any variation at all for all t at both ends, x equals 0 and x equals L. Before we go ahead, we have some variation of the Lagrangian. Variation of the Lagrangian has to be done by considering the fact that Lagrangian is a function of phi, that is a scalar field, and we do have derivatives of the fields, because the Lagrange density function for the vibrating string was 1/2 rho partial time derivative squared, and minus 1/2 tension multiplied by partial spatial derivative squared. Therefore, the variation should be made in terms of these three variables by making use of chain rule. We recall that the equation of motion in the continuum limit was the wave equation. We If we do the right thing, then the equation of motion, that is Euler-Lagrange equation motion, after our derivation should be the same as this wave equation. Alright, so by making use of this constraint for there is no variation for the endpoints of t and endpoints of x. Let us vary the Lagrange density. Lagrange density function is a function of phi, and it's a time derivative and spatial derivative. Therefore, by making use of chain rule, we take the derivative with respect to the field, derivative with respect to the time derivative of the field, and the spatial derivative of the field, and then multiply that factor with the variation of those derivatives. This one can be computed in such a manner. We will call that the variation of the time derivative, just like what we have done with the single particle theory. Delta Q dot was time derivative of variation in the Lagrangian formalism for a single particle theory. So we pull out this partial time derivative outside, and we take the time derivative of the variation of the field. The same is true for the spatial derivative, and we replace this one to be with the variation by taking the partial derivative of the variation of each scalar field. Therefore, we have these two contributions to be rewritten in this form, and the integration by part can be applied if I make use of this representation. So pull out the time derivative outside and then subtract the additional piece that has been added. Therefore, at the end of the day, we have this d phi contribution, d phi, the three terms proportional to delta phi variation altogether, and we have these three pieces that will eventually obtain on the left side of the Euler-Lagrange equation. And we have these two surface terms, and let us consider the treatment of this total derivative. The variation of the action should be the integral over time and space for the variation of the Lagrange density function. As I already stated, this part, this is a usual part, and multiplied by the variation. And we have the contribution of total derivative with respect to time and total derivative with respect to space. And this time integral can be integrated out, and we end up with x integral. But after that, we have values. This variation evaluated at t equals t2, subtracted by the conjugate momentum piece and variation at the endpoint at t equals 1. The same is true for this total derivative with respect to x, that x integral can be integrated out, and we end up with the time integral. So after integration, we find that endpoints at x equals L and x equals 0 is to be substituted. Because of the no variation at both ends, we have all these contribution vanishes. Therefore, the variation of the action is the integral over this double integral of this multiplied by arbitrary variation. And if I impose the least action principle, variation of the action should vanish for any arbitrary variation of the field. Therefore, this expression in the braces must vanish, and this is the equation of motion. Let us make use of the Lagrange density. This integral, this derivative should be done by making use of chain rule, we have 1/2 rho that are constant, and by chain rule it is 2 times this one, right? And then this one is the same, so that's fine. So that's a rho times the first of the time derivative of field. In the case of x, we have x derivative dependent piece, that is potential energy. The result is minus tau. Phi is a spatial derivative. If I substitute this one into here and this one into here, we find the wave equation. Again, the speed of wave propagation is a square root to tau over rho. That is identical to the original expression. So it is completely true. We find that this least action principle also works. We can further extend this method to the case of membrane vibration. Membrane vibration problem has a little bit different structure because the oscillation of membrane can be understood to be the membrane is on a surface, and let us divide into many stripes and consider the nearest neighbor of a single point along the x-axis and along the y-axis. In this case, we have to consider the width of each stripe. Okay. First, let us consider kinetic energy. Kinetic energy. Before we consider that, the mass can be evaluated by integrating over the area. So it is good to define the area mass density per unit area. And transverse displacement at position x and y is again treated to be the scalar field phi. All right. And we have transverse displacement with the two indices, J and K. J and K stands for the x position and y position. For simplicity, we used identical spacing for horizontal and vertical directions. Our kinetic energy can be computed by summing 1/2 m q dot jk squared. Let us divide by d squared, spacing squared, and d squared multiplied by. They are the same. And this d squared is actually the area element, and m over d squared will be mass over area, that is area mass density. Therefore, in this case, the kinetic energy is expressed as a double integral over x and y. And the potential energy can be computed in this way. We consider the force due to the variation along the x-axis and y-axis. The contribution of x-axis and y-axis to the vertical displacement will be like that. And here, this mass is to be understood as the area mass density multiplied by the area. And this dx dy is treated to be d and d. So d squared will be considered in here. And the two contributions, the left-hand side will the qjk double time derivative and mass. And as I told you, this mass is to be treated to be the areal mass density multiplied by the area of the differential. The contribution of the force along the x-axis, the variation of the variation due to the x-axis and y-axis. And again, these are double derivatives along the x-axis, and this is the double derivative for the y-axis. However, we have a vector tau over d that obtained in the case of a string along a single one-dimensional case, but we have to multiply dx and dy. That means d squared to be multiplied. So we divide by d squared again, end up with the overall vector. We have an overall vector tau over d to be here. So d squared appears in the denominator, d squared appears in the numerator. So we do not have to absorb to other places. D should be here. So this D means tension divided by per unit width. So that is so-called the surface tension. Therefore, our equation of motion reduces into this form, and let us divide this dx dy to find out the equation of motion. And in here, in the case of surface wave, the speed of wave propagation is not tau. In the case of vibrating string, it was tau over rho, and this is tension, and this was a linear mass density. However, in the surface wave, it was this gamma. Gamma is a surface tension, the tension for unit width, and this is a mass density per unit area. That is different. Okay. All right. So let us compute the potential energy of this surface case. Fk. Let us recall the one-dimensional case. We had the force, and we have tension divided by spacing and this vector. From this, we were able to integrate over the coordinate qk and repeatedly for the other coordinates and find out the common contributions to find out the potential energy U that depends on every coordinate. Yes, we have only a factor of 2 appears, and we just square everything. In a similar manner, we have the force due to the x-axis and due to the stripe of y-axis, and then replace this one with 1/2 square. 1/2 square. Okay. After that, we find that we have tau over d, and we need the d squared in the denominator to have a square of the derivative. Therefore, we need to multiply d squared. That d squared is an area element of the infinitesimal area element. Therefore, this one is x derivative squared, and this is a y derivative squared. You know, this is x coordinate difference and this y coordinate difference. And then tension divided by the spacing is to be replaced with the surface tension and the area dx dy integral. Thus, the Lagrangian is kinetic energy subtracted by the potential energy, and that is integral over dx and dy. As a result, Lagrangian density is of the form. It's quite similar, but we have two pieces, x derivative squared and y derivative squared. We know in the case of string vibration, we have a single integral over x. So this Lagrangian density and the Lagrangian density for the string vibration, these two different dimensions, are different. And anyway, the Lagrangian has the dimension of energy, but Lagrangian density depends on the dimension. So that's the reason why we had a mass density per unit area for this membrane vibration. This is tension per unit width appears in this membrane vibration. In the case of the string vibration, we had linear string vibration. We had 1/2 linear mass density and time derivative squared, and tension itself. But here, tension per unit width, and not a linear mass density, but areal mass density. That is the difference. But mathematical structure is quite similar. But we are considering physics problem. Be careful with the dimensions.